Have you ever left a glass of milk out on a hot day only to find it turned sour the next morning? Or noticed how an iron nail turns reddish brown when left in the rain? Or maybe you've watched fireworks light up the sky with vibrant colors. These aren't just random changes, they're chemical reactions happening all around us. But here's the real question: how do scientists record or communicate these invisible transformations? That's where chemical equations step in. They're not just formulas, they're the universal language of chemistry, revealing what's changing, how, and why. So, what exactly is a chemical equation? Think of it like a sentence in the language of chemistry, where we describe what substances go in and what new substances come out of a chemical reaction. Let's look at a classic example. Imagine burning a strip of magnesium ribbon in the air. It glows with a dazzling white flame and forms a white powder called magnesium oxide. First, let's write this in simple words. Magnesium plus oxygen gives magnesium oxide. This is known as a skeletal chemical equation. It gives us the basic idea of what's happening, but it still needs a little fixing. We'll get to that in just a moment.
Now that we've written a chemical equation, let's make sure it follows one of the most important rules in science, the law of conservation of mass, which says mass can neither be created nor destroyed. In simple words, whatever atoms we start with, we must end with the same number. Let's revisit our skeletal equation. Magnesium plus oxygen gives magnesium oxide. Let's balance it step by step. Step 1. Count the atoms on both sides. On the left, 1 magnesium atom, 2 oxygen atoms. On the right, 1 magnesium atom, but only 1 oxygen atom. It's not balanced yet. Step 2. To balance the oxygen, place a 2 in front of magnesium oxide. On the right, now we have 2 oxygen atoms on both sides. But look, magnesium is now unbalanced. We have 2 on the right, but only 1 on the left. Step 3. Let's fix that by placing a 2 in front of magnesium on the left. Now it's balanced. We have 2 magnesium atoms and 2 oxygen atoms on both sides. This is a balanced chemical equation, simple, clear, and scientifically accurate.
Now let's take our chemical equation one step further and make it even more informative. We do this by adding the physical states of each substance involved in the reaction. Here's what they mean. S stands for solid, L stands for liquid, G stands for gas, AQ means aqueous. That's when something is dissolved in water. Let's apply this to our balanced equation from earlier. This tells us that magnesium is used in solid form, oxygen is a gas, and the magnesium oxide formed is also a solid. By adding physical states, we give a clearer picture of how the reaction actually occurs, not just in theory, but in real conditions. Now let's bring chemistry out of the book and into real life with an exciting experiment. Take a strip of zinc metal and add a few drops of dilute sulfuric acid. What happens next? You'll see bubbles start to rise. That's hydrogen gas being released. Let's write this as a chemical reaction. Zinc plus sulfuric acid gives zinc sulfate and hydrogen gas. Let's quickly check if it's balanced. Zinc atoms, 1 on both sides. Hydrogen atoms, 2 on both sides. Sulfate group, 1 on both sides. Perfect. This equation is already balanced. It's a simple reaction, but a powerful demonstration of how reactivity and gas formation work in real chemistry. Always remember, try this in a supervised lab setting for safety. Visual suggestions: close-up animation of zinc strip dipped in acid. Hydrogen bubbles forming at the metal's surface. Temperature indicator slightly rising. Side-by-side display of word equation and symbolic equation with check marks showing balance. All right, it's your turn to apply what we've learned. Let's balance a chemical equation together. Here's the unbalanced reaction. Fe plus H2O gives Fe3O4 plus H2. Let's go step by step. Step 1. Balance the oxygen atoms. On the right side, Fe3O4 contains 4 oxygen atoms. So, to match that, we need 4 water molecules on the left. Now, oxygen is balanced. Step 2. Balance the hydrogen atoms. 4H2O means 8 hydrogen atoms on the left. So, on the right, we need 4 hydrogen molecules to match. Hydrogen is now balanced. Step 3. Balance the iron atoms. Fe3O4 has 3 iron atoms, so we add 3 Fe on the left, and that's it. The equation is fully balanced. Chemical equations are more than just symbols and arrows, they're the universal language of chemistry. From understanding how medicine works in our bodies to how fuels burn, or even how plants grow and food is digested, chemical equations help scientists, doctors, and engineers make sense of the world at a molecular level. Let's do a quick recap. Chemical equations represent real chemical changes. They must be balanced because matter can't be created or destroyed. Including physical states gives clarity to how the reaction actually happens. And like any skill, practice is key. Try balancing just 2-3 equations daily, and you'll master it in no time.